10.4, use inscribed angles and polygons. Once again, we're in a circle, and we're going to do a new type of angle today in a circle. Our angle today is called an inscribed angle. And remember, we had the word inscribed earlier, and it's actually back in our notes again today, so this is going to be a familiar word to us that we're going to see often. So an inscribed angle, by definition, is an angle whose vertex is on a circle and whose side contains chords of the circle. So we have this angle right here where the vertex is on the circle, and these are chords that make up the angle. And what we have is an inscribed angle. So it's an inscribed angle where the vertex is on the circle. We have an intercepted arc, which is the arc that lies in the interior of an inscribed angle and has endpoints on the angle. So that's this arc right here that's in between the two chords that are formed by the inscribed angle. So my intercepted arc is this arc right here. An inscribed polygon. We had an inscribed circle as a definition earlier, but this is an inscribed polygon. Since we're talking about the polygon and it's inscribed, that means the polygon is inside something else. In this case, it's inside the circle. And what's super important here is a polygon where all the vertices lie on the circle. So if I have an inscribed polygon, all these vertices have to touch exactly on the circle to be inscribed. And then again, this next term we already saw as well, the circumscribed circle. And again, circumscribed is similar to circumference, where something goes around. So the circumscribed circle is the circle over here that goes around the polygon, and it contains all the vertices of the polygon. So circumscribed is around the outside, inscribed is inside, and whatever word follows the inscribed is the shape that's inside. All right, so here's our vocab. Let's move on to our first rule here for inscribed angles. And I can't stress enough how much this rule is going to be important as we go in for after today and we go into 10.5 notes tomorrow. Super important that we know what kind of angle an inscribed angle is. So when we are talking about an inscribed angle in a circle, it says the measure of an inscribed angle is 1/2 the measure of its intercepted arc. So this angle right here, this angle, we could call it angle D, is going to be exactly half of the arc it intercepts there, which is arc AB. All right, so one thing I want to stress here is my vertex is on this circle. When my vertex is on the circle, or I'm going to call it on vertex, and you'll see tomorrow why I'm kind of pointing this out now. If I see a vertex which is on, it's going to be, my angle is going to be exactly half of the arc. And that's going to be super important as we go and, like I say, mix tomorrow's notes in. I'm going to keep stressing it today so that when we see our next set of notes, we can remember this one today. Right now our vertex is on the circle, and it's going to equal half of the arc. So let's use this rule to find some missing arc or angle measures. So I have this circle P here. One thing I do want to stress to you is it looks like at circle P I have this diameter RS. Just keep in mind from R to S then, as far as the arc goes, that's 180 degrees. And I'm going to tell you honestly, on this problem, it might not become important, but definitely on your homework, keep that in mind that if you see a diameter, you know that you have 180, and you can figure out parts of that 180 from there. All right, so the first thing they want me to find is the angle S. Okay, angle S is down here. So I look at angle S and I follow its two chords up. Well, my angle S is definitely on the circle, so since it's on, it's going to equal half of its arc. And it looks like the arc that it intercepts in between those two chords there is 60 degrees, so it's going to be exactly half of that 60 degrees, and 1/2 of 60 is 30 degrees. So remember, an on angle equals half of the arc. I'm going to do slight adjustment to these notes if you're filling in. I'm going to move my 60 over. They really wanted me, and again, if somebody's just reading these notes, they want to know that it's going to be half of that arc, which was RT is the name of it, if you want to fill that in that way. Okay, so that's my angle. It's half of the arc. Now let's go to arc RQ. All right, changing color here so it's a little easier to follow. Arc RQ is what I'm looking for. Now, I'm going to be honest, we're going to need this 180 rule. So changing colors one more time to kind of focus us here. I know right now that QRS, this is an angle right here, and this angle is on my circle. The vertex is on. And that is, making sure I can read that right there, 37 degrees. Okay, so remember, and I'm going to write it over here, the on equals 1/2 arc. So if I'm trying to get this arc by itself, I would multiply by 2, okay, to move that. So 2 times my on angle will equal my arc. So if I look, my on angle is 37, so that's angle R, by the way. So if I do 2 times 37, I'm going to get an arc of 74 degrees. So my arc is 74 right there. Now, 74 is a great number. It's accurate. However, it's not that arc RQ that they asked me to find. So to find my arc RQ, I need to remember this little rule I gave you earlier about the 180. If I have a diameter, that whole arc or that whole semicircle is 180. I subtract that Q, again, I need to remember QS there, right? Just if you're thinking about that arc. If I subtract that 74 degrees, the arc I was really looking for, RQ, is what remains, which is going to be 106 degrees. Okay, so I needed to use that diameter. So remember that if you see that dot in that center, you know it's the center of the circle. Remember that you can find different arcs just by subtracting from your 180. All right, let's move on to page 2. All right, we have a circle again. By the way, I do not see a center point. Don't assume that where those two chords intersect in there is the center. Just ignore it. We don't know about the center. We don't need to know about the center to find some of these. The first thing they want me to find is arc HJ. So I come over to arc HJ, and I have chords that kind of cut it off, so I'm going to follow those chords, and I notice that they go to angle F. Angle F is on the circle. And once again, I'm going to keep this in mind every time. On equals half of the arc. Well, I know my angle. I don't know my arc. So once again, I'm going to multiply by 2 to move that 1/2. That cancels. If I do 2 times my on angle, I can find my arc. Well, my on angle there is angle F, which is 39 degrees. If I do twice that, I get 78 degrees. So I know that HJ is 78 degrees. All right, now they ask me to find another angle there, the measure of angle HGJ. Changing colors to kind of follow H to G to J. Remember, dot to dot that. G has to be my vertex because it's in the middle. I'm trying to find that. Well, that is definitely on the circle. And so if it's on the circle, it's going to be half of the arc. So G, or HGJ, either way you want to call it, is going to be half of arc HJ. Well, we just found HJ was 78, and half of that is 39 degrees. So that means angle G is 39 degrees, or angle HGJ. And some of you might say, well, that's funny, we kind of just undid the math we did. Those two angles are definitely congruent, okay? And that leads us right into this next theorem that says if you have two inscribed angles, remember those are angles with their vertex on the exact, on the circle. If those two both go to the same arc, so look at this angle D, it goes to arc AB. If I switch colors, look at C and I follow it, it also goes to AB. If they both go to the same intercepted arc, then those two angles will be congruent. So ADB will also be equal to ACB. So if the two angles go to the same arc, they will be the same angles as well. All right, let's peek at our next example. Move my page up here. Name two pairs of congruent angles in the figure. So they're starting with angle QRP. QRP is this one right here, and it goes to arc QP. So what else intercepts the same arc? Well, if I look, it looks like it can also go to PSQ. They both go to the same arc, so that means that they are going to be equal. So QRP and PSQ are congruent. Changing colors here so we can focus. By the way, let me go back to my green one time here. I do want to focus and make sure you realize we were talking about QRP. This is angle R, QSP, this angle S. So those two are congruent. Now when I switch colors and I say, are there any other angles in the picture that are congruent? Well, I can look at RQS. So RQS takes my angle this way, that's angle Q, and it goes to angle or arc SR. Well, I can also see that if I follow this SR, I can choose a different set of chords that go to that, and that will make angle SPR, where my vertex is this P right here. So again, we have two sets of congruent angles. So if two angles go to the same intercepted arc, those two angles will be congruent. All right, let's look at our checkpoints and see what we can figure out here. I will tell you that a lot of your homework worksheet is going to look like these checkpoints. You're going to see some numbers. They're going to ask you for missing arcs or angles. So first, let me focus on what I'm trying to find. On number 1, I'm trying to find the measure of an angle GHJ. So I follow GHJ. That's this angle right here. I do want to stress that is a diameter. That's great to know. I might need that. I might not right now. So it looks like this angle I'm trying to find is on my circle. On equals half the arc. I'm trying to find the angle. This is my on angle. So I need half of the arc it goes around, it intercepts. My angle is, is 100 degrees. Half of that is 50. So my angle of GHJ equals 50 degrees. All right, moving on to number 2 here. For number 2, I'm looking for arc CD. So here's my arc CD. So I follow my arc back to the angle that created that or intercepted it, and it looks like I'm looking at angle B. Remember, on equals 1/2 arc. If I fill in what I know, my on angle is 40 degrees. I'm looking for the arc, so if I want to find the arc, I need to get rid of that 1/2 by multiplying by 2. Those cancel, and it looks like my arc needs to be larger than my angle, and I get 80 degrees. So it looks like 80 degrees belongs to that arc CD. And I will tell you, the more you label your pictures, especially when I get some bigger pictures in the homework, the better it is. So when you find answers, if you can, label it in your picture, especially if you need to use that same picture for multiple answers down the road. All right, last one on this page. I'm looking for angle RTS. Again, don't be afraid to dot those names. So start at R, go to T, then to S, and that kind of stresses for you that angle T, that middle letter, is the vertex of what I'm trying to find. Angle T looks like it is on the circle, so the on is going to be half of the arc. But when I look, I don't have my on angle and I don't have my arc. Or do I? Well, it looks like I have a second angle that also goes to that same arc. If my angle of 31 right here goes to the arc, I can double it to get 62. And then I can use that 62 again to get my exact same angle down here. And I take half of that 62 and I get my on angle is 31. Remember, my on is that angle RTS is 31. Now, did I do extra work here? Possibly, because if I go right back up to my last theorem, it told me that if I see that both of these angles, angle Q and angle T here, go to the same arc, then they're going to have the same measurement. So if I know that, I could have just gone right away and said that that angle RTS is 31 and skip the middle work. But if you want to label your arc and then get your angle, there's no problem with that. It's just a little extra steps, and it reinforces the rule as well. Moving on to page 3. All right, this rule here is one that's going to come in really handy, but it's one that we kind of forget sometimes. But the thing is, if we kind of forget it, it's okay. We'll still be able to figure things out. Okay, if a right triangle is inscribed in a circle. Now, quick reminder here. I have a circle. And remember, the definition of an inscribed shape inside says every vertex has to touch the edge of the circle. So if I try to draw a right triangle inside my circle, okay, so I'm trying to make sure there's a right angle right there. So that's what I'm trying to do. I'm trying to make sure I have a right angle or a right triangle inside my circle. Then the hypotenuse, this hypotenuse of my right triangle, will always end up being a diameter. Let's stop and think about this. Here's my inside angle, my on angle. If this on angle is 90 degrees, okay, if my angle is 90, the arc it intercepts has to be 180. And that's why this is always going to be my diameter, because my diameter cuts my circle into semicircles and forms that 180. So the same idea is, if you have a diameter and you can draw a triangle using that diameter, you're always going to draw a right triangle. So that's what this theorem is telling us, that when my angle equals 90 degrees, if and only if this AC here is a diameter. So if you have a right triangle inscribed in a circle, you're going to end up with the diameter as the hypotenuse. Or if you flip it and say I have a triangle inside my circle and it uses the diameter, then it has to be a right triangle. All right, next example, probably not one of my favorite examples, but I'll kind of walk through it a little bit with you so you kind of understand here. We're talking here about a security camera, and the security camera can turn exactly 90 degrees from whichever direction or whichever way you set it up. You can get a 90-degree rotation. So a lot of people say, well, let's put it at the center of the wall. If we put it at the center of the wall, it can go to this corner, it can go to that corner. Great idea. You end up with equal measures here. But the one thing they want you to know, that you can actually move this camera, because if you always get 90 degrees, that 90 degree could come from inside here, and it could still cover the same thing. Let's say that this area here is a doorway that it wants to hit. You can move that directly in the middle of the doorway. You could come to the left a little bit. You could come to the right. Anywhere on this semicircle would form a kind of right triangle, is what it's trying to state here. Okay? I'm going to leave it at that, not even going to fill in the words. So just kind of a real-world example of using that right triangle inside of a circle. All right, last and final note on this page, and again, super, super important one. Mark it, star it, make sure you know to come back to this. We have a quadrilateral, can be inscribed in a circle. Okay, so we think about it. Circle, quadrilateral, 4 sides, all of those vertices have to touch the corners. And you can see my accuracy in drawing is terrible right now. Well, don't forget, a quadrilateral is always 360 degrees. We learned that back in chapter 8. And we know, so all those angles have to add up to 360. But not only that, we get this extra rule of the opposite angles will be supplementary. So my angle D across from my angle F, they don't have to be the same angle, but the two of them together are going to equal 180. And then we have, changing colors here so it kind of starts up. I have angle E over here and angle G over here. When they're across from each other, those two are going to equal 180. So opposite angles in an inscribed quadrilateral will always equal 180. And that is super important, and it allows us to solve all kinds of them when we know that across from each other, inside a circle, those opposite angles will always equal 180. They do not equal each other. They could, but they usually don't equal each other, but they do. All right, last and final page. Using all of our rules combined, we're going to work on our inscribed angles and these inscribed quadrilaterals at the same time. Find the value of each variable. So when I look at A, I have a circle, I have an inscribed quadrilateral. So right away, I know the opposite angles are going to be supplementary. They're going to equal 180 together. And I can't stress enough, so many people just want to set them equal to each other. They're not equal, but together they equal 180. So if I start with angle P and angle R here, angle P is 100, angle R is Y. I don't know what it is, so I know they both equal 180. I take my 100 plus Y equals 180, so Y would have to equal 80. In the same picture, I know the opposite angles Q and S, so Q over here is 88, S over here is X. They're opposite, they have to add up to 180. Subtract 88 from 180, and I know that X equals 92. Quick, easy rule if you remember it. If you don't, you might stare at that for a long time and not know what to do. So make sure we remember that rule. All right, second example. I have, again, a four-sided figure, a quadrilateral inside that circle. So no matter how it looks, opposite angles straight across from each other are going to be supplementary. So angle J and angle R are angle J and angle L are straight across from each other. So together they equal 180. So I have 8x plus 4x equals 180. 8x plus 4x is 12x. To get x by itself, I divide by 12. Little calculator help on this one. X equals 15. Now another one, I have angle K and angle M, and they are across from each other, so they're going to be supplementary. They're going to add up to 180. Both of them are 3y, so 3y plus 3y equals 180. 3y plus 3y is 6y equals 180. And dividing by 6, little calculator help. Josiah, you out there? I could use your help. All right, and divide by 6, and y equals 30. All right, just a quick note. I'm going to plug these back in. I should have done it on A. I'm going to just kind of skip that, but go to B. If I plug in x equals 15, 4 times 15, 60. 8 times 15 is 120. When I add those together, do they equal 180? They do. All right, let's plug in our y of 30. 3 times 30 is 90. 3 times 30 is 90. Do 90 plus 90 equal 180? They do. By the way, anybody recognize this special quadrilateral that has one set of opposite angles congruent? If you said kite, you're right on. Nice work from Chapter 8. All right, before I move, I might as well do this one in the margin. We know the ones in the margin are lots of fun and good practice for us. So let's peek at this circle here. And by the way, if and when this is on your homework, because you're going to see one similar, it's just going to say find the values of x and y is what our job is here. All right, so I see x down here. It's on angle C. Angle C is on my circle. I follow my lines all the way up. All right, so for x is on my circle, so that should mean it equals half of its arc. It'd be nice to use my inscribed quadrilateral, but I don't know the opposite angle, so it doesn't help me here. So it looks like I'm going back in my notes a little bit, using the on equals 1/2 the arc. So my on is my x. It's going to be half of an arc. Now here's the deal. Don't forget, when I follow my lines, my arc is this entire thing. So make sure you don't just use one of those numbers. I actually need to use 75 plus 108. I have to add those two together to get the full intercepted arc. All right, so a little math help here. 75 plus 108. That takes me to 183. And I take half of that, and I get 91.5. It's fine to get decimals as long as they're accurate. We're good. And I do get 91.5. All right. Little space here so we can solve for y. All right. Solving for y. So I find y. It's up here on angle B. It's actually 2y. I look across. I don't know that angle, so I can't use my inscribed quadrilateral rule. But I can follow my chords. And once again, the vertex of this angle is on. So on equals half of its arc. On angle is 2y. Half of the arc. So again, follow between these two blue lines is my full arc. I have to find that full arc, not just part of it, but the full thing. And that's 108 plus 104. So I get 212. All right, so I've got some math to do here. Half of 212 is 106. And I still need to get y by itself, so I need to divide by 2 again, and y equals 53. So just be careful when you're finding half of an arc. Make sure you find the full arc. If you can't find the full arc, ask yourself, can I find a diameter and subtract from 180 to get a measurement? Can I take my full circle of 360 and subtract to find an arc, something to that effect? So always use the previous rules we know to try to work to find what we need. All right, 2 more problems to go here. I have a right triangle is inscribed in a circle. All right, circle, trying to draw a right triangle. Make sure I get a 90 degrees right there. It says the radius of the circle is 5.6. What's the length of the hypotenuse of the right triangle? At first glance, it looks like one of those mystery, like we forgot what we were talking about. We want to know, what is this hypotenuse? They gave me the radius of the circle, but I want the hypotenuse of the triangle, so it's 2 different shapes. Don't forget the rule we learned on the last page. If you have a right triangle inscribed inside of a circle, that hypotenuse has to be the diameter. With that rule, we can take this radius of 5.6, put it here on this side, and we know that this side's also 5.6, and you can't read my writing on there at all. I should just take those away. But if the radius is 5.6 for the diameter, I'm going to double that. And I get about 11.2 for my diameter, or my hypotenuse, because they are the same thing. All right, last and final example here on our notes today. Find the values of A and B. Well, I have a circle, and inside is an inscribed quadrilateral, and I know the rule is opposite angles are supplementary. So I'm going to start with A over here and C over here. They're opposite of each other. So I know that A plus C should equal 180. A is 5A. C, we already know its measure is 90. And I'm solving here for A. Subtract my 90. 5A equals 90. Divide by 5. And A equals 18. All right, trying to solve for B here. Same picture, but obviously we're working with a different set of angles. So now I'm working with B and D. They are opposite of each other, so B plus D has to equal 180. B has a measure of 4B, and hopefully we can tell it's a B and not a 6. And D down there is 96. And we do know that's a D, right? Don't ask me why that looked like 9. Equals 180. Subtract the 96, and 4B equals 84. Divide by 4, and B equals 21. So inscribed angles, what I really want you to remember is that if the vertex is on the circle, it's going to be half the arc. So remember, half the arc, and if you happen to have a chord that actually diameter, don't forget that this whole thing is 180. So find one piece of it and subtract from 180 for the other piece. I think that should give you the hints you need. I can't stress enough, when you find your picture, mark them up. Make sure you mark down every measure you already know. It'll help you find the measures you don't know. So make sure you do that. You have a worksheet again today. Email me, send me questions if you're not sure on something, and I'll try to get back to you with feedback so you know if you're on the right track.